so funny. You just see your arm. I am Doc Ock, and I'm taking over New York. Spider-Man won't be able to stop me and Steeler Man.
I have. Is this dark because we're doing line equations?
I'm so scared.
All right. Spooky. I could go to everybody.
What is light?
Particle of light.
Long time ago, scientists came up with this idea of what we could do is we could separate everything into two categories: particle or wave. Now, my question to you, children. What is light?
Something you're holding on the ceiling right now?
Ooh, me.
Y'all gonna give me an idea.
Lumens.
John.
Oh my God, that's right.
Obviously, I didn't drink anything, I swear.
Well, light is
My computer's so slow. Don't give the answer. Okay, good.
light
Yes.
is photons, which are particles, right? They have energy but no mass.
I asking you.
I can't tell who you're pointing at.
Yo.
Yeah, what's up?
The Lions fan?
No, not you. Him.
Me?
Doctor Ock.
Yes, sir.
I answer.
John goes. You go particle.
I say particle.
Okay.
Now I can't see though, because I have blue eyes and they're real sensitive. Thanks. Yeah, there's a dot.
Gazzy, say wave. What you say?
Let's see a little man. He's got little arms. Hope he's getting bigger.
What you say?
Mine is kind of shaped like a frog. That looks like a butt.
Give me an answer.
That looks like a sword.
I want to know what you think. Particle or wave?
Particle.
I said particle up wave. I'll totally
I
jack that up.
thought you said
Here, I'll fix it
I thought
for
you
you.
said particle or
Yeah, get that for me, Mr. Ellis. Take that F and like erase it. Make it an R.
Make it
Back in
an R.
I'm sorry, Mr. Jackson.
Shut up, Steeler Man.
Okay.
We
there we
made
go.
ourselves that teacher quick because that's not.
I need a response from the class. So, I ask you, how many of you think it is a particle?
I'm raising my hand. Well, hand.
You can only raise one, Doc Ock. Only one. Wow, so I got 5 for particle.
6.
How many of you think it is a wave?
Everybody else.
Look at that. Is that a raised hand, Amelia?
Yes.
Okay.
It's a no. She's been through like saw trip or
I
something.
had hair goes around. I'm not supposed to take one out.
She went to Saw 5.
Alright. I'm going to tell you something. It's very intriguing. I have the flashlight on for a reason. I have the light switch off for a reason. There is a very nice characteristic when it comes to light and when it comes to waves. Oh, that's bright.
Jesus.
Sorry.
That's brighter than my flashlight right now. Oh. Ow. Burning.
Okay. What happens if I would decide to take a rock
Getting smaller.
and I yeet that thing into a pond of water? It goes splash and it starts
Drowning.
wave. From the moment, from the area where it impacted, you see it radiating out. Yes?
Yes.
So it's going to radiate out. And what is characteristic? What is something we see with that happening? As it goes out, it gets
Bigger.
bigger. So you can say that waves expand. Yes?
Yes.
Sure.
So this is the reason I have my flashlight.
Okay.
I introduce you to the first reason of why light is a wave.
Yes.
Here's my flashlight.
I remember taking a definition on something like that. I remember it said wave.
So, you see how small of a spot that is? That's how the light coming from my flashlight starts, right? But as distance comes into play, what happens?
It gets bigger.
Bigger, it expands. See? I can light that to like half the room. I don't even think this is the brightest setting on this thing.
It's alright. I'll create the sun.
Oh yeah.
I have seizure problems. I'm just kidding, I've never had a seizure.
Yeah, that's definitely the brighter setting.
Yes.
So,
Very.
you see the light expand. So we would say that light is what?
Wave.
A wave. Very nice. Now, we're going to start focusing in on some waves. But before we get into talking about them, you need to know some things about waves. Like, the good thing is what a wave looks like and the parts of it. So let's make a wave. Whew. I'm blinding myself. Turn this thing down.
It's hard to make a wave, Mr. Hall.
Mr. Hall, working problems.
Let's make a wave.
We're making a wave.
Making a wave.
Stop it. Stop it. Okay, so we have a wave. There is the wave. Now, everybody watch your eyes.
Yeah.
I'm going to turn the lights back on before people think we're out of
Stare
power.
directly at the light.
Oh God.
You don't.
Oh.
Oh.
Yeah. Hey, at least we know if you're in 8th period and we run out of electricity, Mr. Hall got you. He always has his flashlight. You're welcome. Did you have a question?
Would it be possible for me to take the first quiz today?
You brave soul. Sure, why not?
So
Is that what you want to do?
that is what I want to do because partial credit is better than zero credit. Technically,
In theory.
if you could.
Equally balanced as all things should be.
Allegedly.
Bro,
Okay.
Why don't all the teachers have their big apples?
Mr. Hall,
You'll see, I think it was Miss Hall, it was like Miss Hall or Miss Adams all bought us an apple and left it on our desk over the weekend with a note. They're telling us thank us for everything we do for our children. Everything we do for you. I work so hard for you, yeah? See?
any chance do you have a gold, like, ball?
No, I do not.
I turn it into
Does
the
it
sun.
matter how big of a wave that is?
No, as long as you got a wave, because what we're going to do, we're going to label the parts of a wave here. Alright, give me a second, I'll give you a periodic table before I do that. Oh, no. I'll always give you a fresh one.
Oh, okay, that's good.
Okay. Number 6 is what I'm going to start you with. Because number 6, I have back here. Here is what A is. Here's what B is.
Okay.
Okay. You'll want that. You'll also want one of these. Alright, so let's talk about a wave. So there's some points on a wave that we care about. So the first one is the highest point. Now the highest point, does anybody know what it is called?
The summit.
What's your wave?
Look at us, but no. Does anybody know what the highest point on a wave is?
Correct.
The crest.
Y'all been watching my videos?
No,
No, I just know that. I
I was,
figured
I
we
was,
just
I was
had
asking a
waterway.
question about a ride. That's why I was.
You're okay.
I got
It's just something you said earlier made me go, here going ahead of the class.
No, I know a lot of things.
Okay.
It was on the board.
I know too many. It also was on the board this morning, but we don't talk about that.
I was on the board yesterday.
I saw it on the board in the fourth period.
You're cheating.
But I also knew
I
that.
sure am.
Alright, so the top is called the crest.
Gotta do good to win. You won't understand. Act broke to stay rich.
Now, at the risk of, looking stupid because you already know the answer because you already looked at the board, you cheaters. What does the bottom
Stay mad. Stay mad.
Yay!
The plummet.
Trough.
Oh, I was gonna say the
I
trench.
could have guessed that.
I was gonna say the trench.
Yep, the bottom is called a trough. This is how I like to remember the bottom of a wave. What does a pig eat out of? Trough. Where's the trough? At the bottom.
Yeah.
So, these are very important points. The crest, highest point of wave. Then we have our trough. What is our lowest point?
It's probably
Now, I give you these for a reason, to bring you into an idea, because I want you to have an idea of what's going on and what you're talking about, terminology being used. And here is a big one. You will become used to this, and it will become one of your friends. Not your BFF, but it will become a friend, because you best know how to use wavelength. Wavelength is the measurement between two same points on a wave. So what that is saying is if we want to find the wavelength of something, of a wave, if you want to find that wavelength, it has to be the same 2 points that you're going to use. So this is where the crest and the trough and everything comes in really good handy. So a lot of times we're going to try and find a wavelength of something, we're going to measure crest to crest. And then sometimes, because, we like to live on the edge a little bit in the scientific world, we'll go trough to trough. Now, I know what you all are saying. Mr. Hall, that is no straight line. Yes, I did not make a nice wave. I apologize. That should be a straight line because the amplitude is bigger there. Don't worry about the amplitude. I'm not going to go into that with you. But I could measure there, but I have to do the same point. It has to be the same point at both cases. So, you will see the wavelength as the distance between those 2 points. Now there's another word that should become familiar to you. It is on your electromagnetic spectrum. It's very nice. This also must become a very good friend of yours. See?
frequency.
Frequency. Now the frequency is how often the wave passes.
Pardon the interruption, but I need to see any morning CTC student that has been vaccinated in the office. That's any morning CTC student that has been vaccinated. Please come to the office.
In an amount of time. So this is all about how frequent something's taking place. Frequency is all about how often. Frequent. Alright? Now when you look at this, I'm going to introduce you into a unit. And I want you to get introduced to it so it'll make sense. Hopefully a little later. I don't know how far we're going to get. But the number of waves, because that's how often, how many of those waves are passing over an amount of time. Now when you look at this, I want you to think strictly of units right now. So when we start looking at this, I have the number of waves, which when you look at that,
Sorry. I didn't tell Betty I'm leaving. I can put it to her earlier.
oh, you're fine.
Wherever she got. I'm leaving
She's
to go
doing
get Avery so we can meet back up with Miss Cole.
I
I dropped her off.
You
But
good?
can you come in this way
Yeah.
to get your stuff?
Yeah.
Okay. Thank you.
What? So the number of waves that we are looking at, that's just a number. Okay? So let's say for a number, if you want to simplify it as much as you can, we put a number 1 up there. He was number 1.
I have 6 arms.
I'm wearing shoes.
Good. Touche.
Ty, I have a question for you. Mr. Hall ever mentioned that this class builds on top of itself, stuff never leaves,
Yeah.
No, not
and
really.
it just keeps coming?
I don't recall.
Are you getting ready for a second of her?
What is the international system of unit for
Second.
time?
Second.
Seconds.
Yeah, a couple minutes.
Yeah, a couple hours if you really think about it.
So we're looking at seconds.
Milliseconds.
So this would be 1/2. Now, any one of you that wants to accuse me of this, get your phone out, take your picture, and take it to your math teacher and let him show you. Mr. Hall, no breaky the rules of mathy, okay? This is equal to inverse seconds. It's an exponent.
It's like the opposite.
So it's a s for seconds to the -1 power. Now, I know what you're thinking. Why did my s get so much bigger? It's because I
Cynthia
got so
Atkins, Amelia Muscari, please set a Taylor Atkins row.
I got so excited to talk about it that I wrote the figure. I thought it did not grow. Now, this is where some of you are probably going to look and say, wow, this guy, he was a prophet. He prophesied what was going to come when we did the mathematics with this. Because this is a fancy number, a fancy unit for what we call as hertz. Just watch that Cat 5 cable sitting there. Let's see.
I'm glad I took true. Is that an H?
That is an H.
Ain't hurts like sound?
It is used in sound. You know what it deals with? The frequency.
Yeah, the frequency. I mean, that's here.
Yeah. That's a little z. Yeah, on my z's I put a dash through it. I don't know why. I just started doing that.
So it don't look like an S.
Yay. Now, you've been introduced to this. And I've shown you today that light is a wave. Now today I want to teach you as to why. For me to do this, can you two please do me a favor? Do not ruin my magic of what will come later in the class. You will pick up on it as I say it, okay? Because you two got me a little nervous with things that you've said that I'm like, man, you're going to steal my thunder.
What can I say?
Yeah.
Don't steal his thunder.
I want to introduce you to Thomas Young. Now, Thomas Young is very famous for what he did in 1801. Whenever it was 1801, Thomas Young came up with a very, very, very famous experiment. There's one that shall come back later on in this class. If you walk on any university and you say this experiment, I promise you, you'll find people that can talk to you all about it. Today is Mr. Hall's turn. This is called double slit experiment.
No, that was me. My pencil stopped working. I wasn't acting you. I wasn't saying you were wrong or something. My pencil stopped working. It made me upset.
So, the double slit experiment is very famous because what it does. It's going to prove that light is a wave. I introduced you to the natural property of waves that expand so that you can get an idea and understand what's happening here in the double slit experiment. So the first thing you need is a light source. Now with a light source, just like my flashlight, it's very bright. I think my retinas are starting to recover. The light source, light will come out and it will what? Expand. So it expands out. You know what? Let me go to the marker box. Don't want to encounter the problems that we faced earlier. Ooh. Perfect. I had to cut it orange. So we got this light source. It emits out light. Yeah. Ooh. Look at that.
It looks like chicken fried rice.
Now this is where it all gets interesting and fun, because a light source emitting is a problem if you want to prove something. So he sticks this wall up. Now the name tells you everything, double slit. This is why we put two slits. One there and one there. It's the double slit experiment. See? Now, here's what happens. This light source radiates out until it gets here, right? When it gets to the wall, what will the wall do?
Stop.
It stops it. But we put two holes in it.
Yeah, it's not working.
So now it's going to come through, but come through where? From the two holes. So this is where it gets interesting. Let's do side, this side blue. So this light comes out and it expands, right? It keeps expanding. The farther it goes out, the more it expands. Everybody cool with that, right? I showed you. You need me to turn the lights off and turn my flashlight back on?
No,
This one.
Got it all.
I think that'll help.
Then let's look at this side over here, the red side. Are you okay?
Yeah.
Okay. We look here. What happens at this spot?
Same thing.
Same thing. Light comes through and it expands. I went to puberty. Did you hear that? I got all high pitched.
Yeah, mine's just kind of stupid. But I can tell what you mean.
That's okay. We want your lines to cross and intersect. So this is what's happening. Light is a wave. So it's expanding out. So these wavelengths are expanding outward. And then you get this interesting thing when you would look at the back wall per se. By the way, anybody that wants to like correct me on this, I'm taking something that's very complex and bringing it very simplistic. So on the back wall, we've seen something take place. Seen something very interesting. Give me a moment while I put my art skills to work. I make you a masterpiece.
Oh my gosh, he's the modern day Picasso.
Oh, I thank you.
Alright, guys. Now it's my time to take over New York. We're gonna go. Nobody's paying attention.
You never thought what you did in kindergarten would ever be useful in high school till now.
Color.
Yay! We color things. Now, there's something special about this. What this is the crucial for the evidence of what we're talking with light and what will later come on in this class. Please do not steal my thunder. Thank you.
I dropped my marker.
What takes place is at these points where you'll see this orange darkened in, you are seeing light. At the areas where you do not see the orange, we would see no light. This is something very special. This proves light to be a wave because this is a very special pattern. This pattern you see here is what we call an interference pattern.
Kind of just skips over.
I didn't think so.
So the interference pattern
Does that?
is what proves light to be a wave. And this is what's happening. Whenever you see an interference pattern like this, what's taking place is areas like this. This.
They cross over.
This. Somehow it did not happen over there, but it's happening, okay? Poorly drawn system.
Where
missed one.
houses?
You missed two.
Missed three. Missed three.
Oh, dear Jesus, help me, Lord.
Two directly in front and one off to the left. Larry.
It doesn't matter.
One right up
No,
there.
it don't matter. They just want to be whatever.
It does matter.
St. Eunice, John.
It's like taking the E off the mall. It matters.
Mr. Ellis, you are fired. Do no longer.
I was fired today.
He said I lost it.
Literally fired.
Here's what's happening in all these areas that I circled. We have interference taking place. Waves have this very special ability. How many fishermen I got in here? Fisher ladies. Yeah. Y'all like wade fishing?
Yes.
Kind of like big fishing.
There was something beautiful when I am smallmouth fishing.
Okay.
When I'm working down through there, and I look downstream, and I see an island in the middle, and the streams go like this. What?
When you're on your kayak, you go down one of them.
Yeah, that's bad, but To me, as a wade fisher, I look and I go, man, I can fish the left, I can come back up on the right.
And you
The
can
fish-
circle around.
The fish are going to be here. But this is what happens. As the island splits the water's moving the same direction, right? So it moves the same direction. When the island ends, the water's still moving the same direction. So what happens? It just keeps going. It doesn't fight. It doesn't cause a problem.
Kind of opened up a little background.
David Bledsoe, Morgan Massey to the
It
office.
keeps going. Now, let's say you have a delta. Got a waterway going this way,
Okay.
and then you got a waterway that goes this way, and they intersect.
Okay.
What happens here?
The waterway coming in this way is going to go.
It's going to go, but what happens is it still has that force carrying it through. It'll spin. It creates problems. It interferes. It's the same thing here with waves. Whenever we look at this, you see this interference pattern come into play. You see it building it up. Oh. We see light where the same points meet up. So a crest and a crest, or trough and trough. This is what we call constructive interference. So that constructive interference, construction, it builds, right? We're building up. The areas where we see no light are points where opposites on the wave hit. So a perfect example would be a crest and a trough. So you see no light where crest and trough meet. This is called destructive interference. Destructive interference is what I like to call in the construction world demo day.
Okay.
Demo day's great. Nothing like demo day. So this is what we're seeing taking place. So, what experiment proved light to be a wave? Double slit experiment. How did the double slit experiment show light to be a wave?
Because there was interference and
Don't know, but
interference
the
pattern.
dude said so. Just
It's an interference pattern.
Interference pattern. Have you guys heard what this means in my room?
Purple marker mean write down important words.
Super, super important. Everything I put on the board is important, but if it's in purple, it should look like a 747 jet is going to land on your paper.
Like wavelength?
And sure, why not?
Be on a quiz.
Well, all
It's
is
fair game for a quiz. It's not a guarantee it'll be on a quiz.
All of this could be on a quiz.
All is fair game.
Weston Massey, Caton Kennedy to the office.
This right here is so important. I'm mesmerized. Sorry.
There's a circle. Oh, okay. Anyways,
Let's have fun. Circle.
it looks like a
Circle.
It looks like what happens when you like drop your slinky a couple times.
So this is what takes place. This is what shows that light is a wave, is the interference pattern. The experiment that showed this was the double slit experiment. It did this by passing light through two slits and letting them interfere and creating that interference pattern on the back. So what is an interference pattern characteristic of?
Waves.
Waves. Because if you want to get a picture of that, now is your time.
I'm true.
That's fine.
I'm true.
I just wanted to give it as an offer because I'm pulling out the eraser now.
Oh no. So scared. I got a picture of it, I never looked at it again. This one.
beautiful artwork.
Let's say we switch it up.
Where'd you get your art degree in?
Whiteboarding class.
Miss G Studios. I helped Miss G build a prom. By help her, I was a student and just did what she told me. Which anybody that has Miss G should know. If she tells you to do something and you're building something, you just do it. She knows what she's doing. So let's say we change everything up. We don't use a light source. Let's say we use particles. Put our slits in. Make the slits bigger. We have a system on the back to track what happens. Now let's say we take two professional bowlers, because I don't mean to brag or nothing, but my bowling skills are awful, and I can't keep a ball straight half the time. So
Did you really?
Well, the key to getting a strike is a curve. You don't want a straight ball.
I've got plenty of strikes with a straight ball, Drake. Don't you question me.
Well, if you want to get it more efficiently, you should curve. It's the correct angle.
Fine, we got Drake. Drake's our bowling expert. Let's let Drake
You
do
ever
it.
talk about
I watched
efficiency
one
when your
do
team
perfect
goes like what,
video,
3 and
okay.
14?
So, if you tried to curve your ball here, Drake, what's going to happen? You're going to hit the wall. You're not going to go in the slit, so we got to go straight.
Well, I mean, if you're pretty good,
We're going straight. So let's say we send bowling balls shooting down through here in a straight line.
Pitching a baseball. That's a good straight line.
What if they throw a curveball?
See, now you're being him.
well, you see, there's other types of curveballs, but they're like a 12 to 6, which takes the straight, it just drops on the wide.
Guys, we can throw a ball a different way.
Well, that's what I'm explaining.
Trying to think of straight balls.
All right, we send particles going through a straight line, hitting in the back. What pattern will we see? Two slits,
Straight one?
two lines.
Of light.
Straight line with two bands.
So it would just be two bands, because it's going straight in.
That's it, because it's going straight and hitting it. It's going
It's
in.
not bouncing all over the.
Exactly. It's just hitting. We're counting your first hit. So this thing's hitting. So what do we get characteristic with particles? Just two bands. This is what shows the difference between a particle and a wave. This is what will help us. Now, I have a question.
Okay.
I'm going to move my chair first. Sorry, I didn't argue earlier. Okay, so we get these two bands. So here's my question to you. We decided, what is light?
A wave.
A wave. So light is a wave. What do we find light on?
The light
Electromagnetic.
board
Electromagnetic.
with visual
Whatever it's called.
Spectrum.
Spectrum.
Electromagnetic spectrum.
Good job.
Thank you.
So the electromagnetic spectrum has light on it, which tells us the electromagnetic spectrum is made up of all forms of
Like
Waves.
waves.
yes,
Energy.
Electromagnetic
energy.
fields.
The electromagnetic wave.
Waves.
Waves.
electromagnetic radiation is the word I was looking for.
Radiation.
Well-
Oh.
So it would bring me into an answer you was giving me, but I wasn't wanting it yet.
In the ballpark.
That tells you electromagnetic radiation are all forms of
Waves.
waves.
Oh, waves.
So all of these are waves.
Yep.
So, when dealing with waves, we have a joy.
Havana Painter to the office.
I want to say something to y'all in the room. That you thought mathematics was leaving this class. It's all good because it's back, baby.
Lindsay Baker to the office.
So, the math that goes into this, I want to introduce you into the two like equations. Wow, I messed that one up. I feel like I need an oxygen tank here today. I'll introduce you into two of them. The first one is one that you'll kind of be familiar with. The first one is C. Not yes. C. Wait before you tell me what it is. I ain't asked that yet. C is equal to lambda times a lowercase nu.
What?
Second.
Are you sure you're not watching my video?
We already looked over those already. We have those on notes. Yeah, they're in here somewhere. Pretty sure we went over it.
Okay.
Right here, wavelength and frequency. Right?
So, yeah, I gave it to you a little ahead of time. Foreshadow. So C is something you're familiar with because of Albert Einstein. E equals mc squared. What is C?
The speed of light.
C is the speed of light. Now, in this class, we care about accuracy and precision. So we don't do that junk with the whole, messing around. If somebody looks at you today, you walk out of here, you know what the speed of light is. They tell you 3.0, you go, nah! No, it ain't. Speed of light is 2.98 times 10 to the 8th power. And what's important, what always matters, what brings identity to our numbers? Units. So the units of the speed of light is meters per second. Now, as you all learned from your last quiz, did Mr. Hall give you Avogadro's number? Y'all got me saying avocado. Did I give you Avogadro's number?
No.
On your quiz, did I give you? No.
No.
What did you have to do? You have to know it. Just like you have to with this constant.
Oh, you're not.
You have to know what speed of light is. Now, lambda is very special to us. Lambda, as I've already told you, is wavelength. You all do me a favor, give me some units for wavelength. Nanometers.
Meters.
Yeah.
Meters.
Kilometers.
Kilometers. The point is, this can go on and on and on. Hey, did Mr. Hall say anything to you about how this class builds on top of itself? And you ain't got to forget anything?
Is that millimeters or
Nanometers. Millimeters still go, doesn't matter. Mr. Hall tell you about how you build on top of it, and everything comes back together.
This is starting.
Can I point something out to you? What's the unit for speed of light? Meters per second. What you think your wavelength got to be in before you do your calculations? Meters, very nice. Now, let's talk about nu. Nu is frequency. Frequency, I gave you the units for.
Hertz.
1/2, inverse seconds, and hertz. Now, I gave this to you like this for a
Daniel
reason.
Road to the office.
Inverse seconds. We're multiplying. So inverse seconds. Look what's on the bottom. Seconds.
Haley Painter to the
What's
office.
wavelength then? Wavelength's got to be, when you do your calculations, in meters. So you got meters times 1/2, which gives you meters over second. It's like the units work together for you. It does. Tomorrow, when you come in here, I have a gift.
It's a practice sheet.
No. I give you the second of the light equations, and I give you one of my favorite numbers. Please have a wonderful day. I'll see you all later. I bring cookies and brownies to flow sites. Alright, so I want to hit on, and this will come back into play later with what we just did in that lab.
Women are probably like you used to.
And I started on the two light equations with y'all.
One of them.
I gave you the first one, right?
Yeah.
Okay, great.
Want to refresh our memory though?
So, yeah, absolutely. So, I want to hit back up on these two light equations, and I'm going to give you the second one. So it's really funny what first period it came up for the first light equation, which is C equals lambda times mu. They're calling it the speed of light is equal to dyno V.
I can see that.
They said that's a dyno, and I'm like, whatever helps you remember it, I don't care.
Reminds me of like the moving.
So, with this, C, as you guys know, is the speed of light. Which is 2.98 times 10 to the 8 meters per second. As a constant, you will have to memorize it, you have to know it. You'll make it your best friend. One important key to stress, the unit, meter. I'm going to use it, make sure your wavelength is in meter. So the dyno, or lambda, is wavelength. And the V is frequency. I'm going to introduce you into one of my favorite ones, because we get to talk about one of my favorite constants. And hopefully your class catches on a lot faster than first period.
We're pretty smart.
Is energy is equal to letter H mu. You boys know what H stands for?
All I know is the H is probably hertz and then frequency.
Energy equals
Energy equals hertz times frequency.
I don't know what H means.
Alright,
I thought it was
it's okay.
hertz.
It's cool.
Hertz is H and C.
E is energy. In this class, in this area, we're going to be looking at, we're going to study and know that energy is in joules.
Ah,
Capital J. H is very special. H is another constant. This one I give a little trick to for you to remember it. The name for this is Planck's constant.
oh, Planks and stuff.
What? Planck's H.
Why that just doesn't make
In
sense?
that world, are you talking about?
Planck's constant. I didn't misspell it.
Why is it?
Planck's constant was named after Max Planck.
Max Planck. That's funny.
Planck's constant is another constant you have to know and have to memory. And the way I like to teach it is 6-point stitch. Yeah, stitch.
6, 3.
You know stitch, right?
Yeah.
That's literally what I just said.
Stitch. Experiment.
Oh, I don't know what his number is.
3, 6.
I haven't watched that movie in a long time.
3.
If I had Wi-Fi on my phone, I'd look it up.
Like
It's 43.
Oh, so close, so close.
6, 6, 7.
42.
6, 8.
Experiment 6 to 6.
66. I was so close.
I've not watched that movie.
Times 10. Negative 34. Listen carefully. It matters. Joule seconds. Joule seconds. It's joules times seconds, not joules per second. Big difference.
Me and Drake thought something was funny here.
Yeah, it's max Planck, but it's the minimum distance you could possibly
It's
ever.
a minimum measure, but it's max Planck. Maximum Planck. It's so funny. It's so funny.
And then you guys know what nu stands for.
Frequency.
Frequency. Here's the thing.
How frequent is your small energy?
My
What?
binder broke.
What?
My binder broke, and I'm gonna take a picture of it and then write it at home.
You're okay. So, what all type of information can you get off the electromagnetic spectrum? There's values that are related together. They're intertwined. First, wavelength. So here's wavelength. It's intertwined with
Frequency.
frequency. But look over here, it's frequency too.
No way.
And whenever we talk about the electromagnetic spectrum, one increases as we went from right to left.
Frequency.
Energy.
Energy.
These three are intertwined together because it doesn't matter what you look at. Any wave of electromagnetic radiation has a certain wavelength which corresponds to a certain frequency, and that frequency corresponds to a certain amount of energy. This is how something becomes dangerous or not dangerous. Does it have enough energy to get in, to cause any damage? Is there not enough energy? There's so many questions that go around with this. Here's the thing I want you to get. You have to see the relationship. What links the two equations together? Frequency.
Purple.
This is how we'll link the two together. If I gave you a certain wavelength and asked you for the amount of energy, can you work to solve it? Yes, because I'm giving you wavelength. You know the speed of light, so you can solve for frequency and plug frequency in here. That will give you energy. If I gave you a certain amount of energy for an electromagnetic wave, you could work backwards and find me the wavelength. Now the fun thing is once you figure out the wavelength, you can use the electromagnetic spectrum to determine first what type of electromagnetic radiation are we looking at. Second, is it dangerous or not? And third, you can identify what color of light it would be. That's why it's important that I know whether you're colorblind or not. So that whenever it comes quiz time, and I'm asking you to identify a color, you're not red-green colorblind, and you're not sitting at 500 nanometers and telling me red. Because if you tell me red at 500 nanometers, I'm going to go, whoa, we got a problem.
If you think about it, when they see the color green, they've always been told that that's green. So even if they see what we see as red, they still think it's green. So technically, they still get it right.
But they can get
My
No,
red
they
thinks you're
don't,
blue.
because then if I give you one
It's all
that's
kind of-
red,
it's all kind of melded together.
if I give you one that's red, then it's red. They're not going to, you see the two different colors. They're literally going to look and say,
They're the same thing.
red, orange, yellow, red, blue, indigo, violet.
What is green?
They'll be like, whoa, why do you have red up there twice? I so thought you were going where another guy went with me one time.
Where's that?
That's where I'm going to stop, because I don't want to start working a problem and then us getting shot. Hey, be in here tomorrow. We're going to rock and roll with these.